Hello everyone, welcome to a new video on electromagnetic fields. In today's video, we are going to see about an important topic, which is nothing but the electric fields from point charges to continuous distributions. As we all know, there are different charge distributions: point charge, line charge, surface charge distribution, and then volume charge distribution. A point charge is the smallest infinitesimal charge that can be represented as point charge, and line charge is nothing but the charges that are aligned on a tungsten filament that can be termed as line charge. Surface charge is the charges on the plates of a parallel plate capacitor, and volume charge is the charges on a bounded body. Any volume or any closed body can be termed as volume, and the charge distribution in that volume is called as volume charge distribution. So we are very much aware of these type of charge distributions. Now we are going to see about how the electric field will be in these kind of charge distributions. So here we are going to see about this is the agenda. We are going to see about the charge distributions and then electric field, how it is being calculated in these charge distributions, and then we'll have some analysis on this. First, we have two images. One is the point charge, the other one is the line charge. So in the point charge side, yes, a point charge represents a single isolated charge concentrated at a mathematical point of space. So the electric field for that is being calculated straightly from a Coulomb's law. So that can be E is equal to F by Q. That is the electric field of a point charge. So whereas continuous charge is a charge that is charges that are spread out uniformly or non-uniformly across a line or a surface or throughout a volume. So continuous charge distribution is any form other than the point charges, like line charge, surface, volume, or in any area. If the charges are spread out evenly or unevenly, that is called as continuous charge distributions. So this requires a different mathematical approach. We can easily, if there are n number of point charges, the electric field of these n number of point charges can be calculated by the principle of superpositions. Let the electric field across the charge Q1 be E1, and for the electric field around the charge Q2 be E2. Then if you want to calculate the cumulative electric field of these two charges, then it can be represented as E is equal to E1 plus E2. So the cumulative value of several point charges can be the consecutive addition of the electric field across each and every charges. But when it comes to continuous charge distribution, the case is different, wherein which we have to integrate the total electric field values. So here, for a line charge distribution, we define the linear charge density. We know that for point charge, you can directly write it as E is equal to F by Q, since it represents a single charge. But when it comes to continuous charge distribution, we cannot calculate the charge, but we can calculate the charge density. So here E can be represented as E is equal to F by Q, but here the Q is nothing but the charge density. We already know for line charge the charge density is rho L, and for surface charge the charge density is rho S, and for volume charge it is rho V. So we have to replace this value in the electric field equation. So we know that dE is equal to the electric field for differential length is given by dE, which is equal to 1 by 4 pi epsilon naught dQ by R square. Since if it is a point charge, it is simply Q by 4 pi epsilon naught R square. If it is a line charge, it can be given by rho L by 4 pi epsilon naught R square, that is being given here. If it is a surface charge, it is rho S by 4 pi epsilon naught r square. Here the rho S can be A vector into dA. For volume charge, it is rho V dV by 4 pi epsilon naught r square. So this is how you can deal with continuous charge distributions, because we cannot simply sum up the electric fields from individual point charges. So we have to divide the continuous charge distribution into small charge elements, which is nothing but infinitesimal values, and then we have to integrate their contributions to the total electric field. So now we can consider a line charge. For example, we can take one form of continuous charge distributions, which is nothing but the line charge. So let us assume a tungsten filament, which is nothing but like a line. Okay, so if we consider this line, finite line segment carefully, we can understand the vector components. So in this line segment, let the length be L and the axis be X, and it is centered at the origin with uniform charge density, and we want to calculate the electric field at the point P located on the y-axis. So here we represents the dq as dx, because that is the axis towards which the line is being projected. So the position is x, 0, 0, and the components for deriving this electric field is dE and DER, and due to the symmetry, the x components will cancel each other, so therefore the y components alone exist. So by integrating, we can get it as L by 2. So here for this line charge, we can have the electric field equation as dE is equal to dL by 4 pi epsilon naught r square. Here this, rho L dL. So here the dL value is L by 2. Now we can have a symmetry about this electric field strength. So the geometry of this line charge, this continuous charge distribution, has a significant impact on the magnitude and direction of the electric field. So by utilizing this symmetry, we can easily simplify the integration calculations. So if we take line charges, the electric field lines generally extend radially outwards or maybe inwards from the line. So for an infinite long line, the field is purely radial and its strength decreases as the length increases. If it is a surface charge, for an infinite plate of charge, the electric field is uniform and it is always perpendicular to the plane. So the field strength will be always constant, and it is irrespective of the distance. So it is not proportional to the distance for a surface charge, and also this case is same for the volume charge also. So when it comes to volume charge and surface charge, the distance is not at all considered for calculating the electric field, but when it comes to line charge, the distance matters more. So for volume charge, the spherical symmetrical volume, the electric field outwards, that projected outwards, behaves like a point charge only. So therefore the inside field depends on the charge distribution within the radius only. So now here is a problem solving scenario. Let us put the put what we have learned so far into this problem, and we can have a short recall about what is the given charge element, and we can calculate it. For a line charge, consider the electric field at a point at uniformly charged circular arc. So the arc is circular, which is nothing but like a line. We are here to calculate the electric field at the center. What will you do? This is one of a real case scenario, and you can consider another scenario wherein which we want to determine the electric field of a uniformly circular area. You can consider any circular disc wherein which you are going to calculate the electric field, or you can have a test case of calculating the electric field on the plates of a parallel plate capacitor. That is also get along with the surface charge distributions. You can take another scenario where we want to calculate the electric field intensity of a uniformly charged sphere or a uniformly charged solenoid or toroid, which represent a volume charge distributions. So these problems can highlight the integral approach, and also it gives the impact or the significance of the correct infinitesimal elements, because we cannot calculate as such, or we cannot integrate as such the entire volume of the surface. So here we have to divide the entire surface into small segments. So there comes the importance of this infinitesimal elements. So far we have discussed about what are point charge and what is continuous charge distributions, and how the electric field intensity equation varies with these kind of charge distributions. So these principles can be easily understood by applying these knowledge into real-time phenomena, like what we discussed in the test cases, like finding the electric field for a parallel plate capacitors, the place of a parallel plate, or for a tungsten filament, or for any lightning rods. So any test case we can take and we can find the electric field intensity for these, so that we can understand the real-time application of these charge distributions and finding these electric field intensity values. So for further explorations, we can go and visit these websites for Khan Academy and MIT courseware, and also we can have a sketching of these charge distributions using the help of coordinate systems, so that we can have a 2D view of how this charge is being, or how this electric field is distributed over space. So I hope in this presentation we have detailedly discussed about what is electric field intensity of a point charge and continuous charge distributions, and we have discussed some test cases also. So through this video you have clearly understood about what is the importance of electric field intensity and how we can calculate for different charge distributions. So in the next video we will discuss about another interesting topic in electrostatics. Thank you. Thanks for listening.